Hey everyone, in this video, I'm going to walk you through how you can model the wings, the tails, the horizontal tail and the vertical tail using H panels and V panels. I'm going to talk about how you can use this control mapping tab to assign, what panel has what control surface, and then how you can perform a quick diagnostic to make sure everything is okay. All right. So in the last video, we covered some of the in Excalibur 3 overview on how you can, input parameters such as CG, fuselage, undercarriage, engines, um, right? So we'll move on to wings and tails in this video. All right. So it's important to know like how the simulator models the wings. Okay. The simulator uses the symmetry. Right. The simulator uses models only the right wing, and then uses symmetry to model the left. Right. So in other words, you cannot model an asymmetric aircraft. Like a slewed wing, like an oblique wing on this in the simulator. It doesn't work. Right. So it works based on symmetry, and you better make sure the airplane that you're designing is symmetric, about this y-axis. Okay, so and the way you model the wings and the tails is using like panels. All right, so you basically put together the wing piece by piece using this like horizontal panels and including the tail. Okay, so here it is. So I'm going to walk you through with an example of C-152, SS-152, right? So the first panel that you're going to model, make sure the first the span of the first panel, is the same as the half of the fuselage diameter, or in other words, the fuselage radius, right? This is just so that you can make sure so that you can model the part of the wing which is actually embedded in the fuselage, right? So, and you can do the second panel, which has the flaps in here, and then the third panel, which has the ailerons. Okay. Now, if you have a section where there is no control surface, as you would in a commercial airliner, then you can use it to model, you can use another panel to model that section as well. Okay. So the important thing is, each panel has its own control surface, right? Doing so, makes it a lot easier to model the aircraft in the same, right? And same goes for the horizontal tail as well. All right. So we'll talk about that later. So again, so far, I hope you guys are clear that you will be modeling the wing and the tail using like the panels, right? And each panel should be associated with at least, should be associated with a control surface, okay? And if you have a panel which doesn't have a control surface, that's completely fine, right? It's completely fine. But you're segmenting the aircraft wing in such a way that, you know, you're covering the portion which has a certain control surface into one panel. All right. Okay. I think I made that clear. So moving on. Yeah, if you click the H panel tab, this is the page you see. Again, you can see there's a lot of information in here. So what I'm going to do is I'm going to walk you through one by one. All right, so that everybody understands what type of information goes into these panels. All right, so right away there we have the sub panels, right? So you have about 10 different panels. Because it's customary to use the first 5 panels for wing and the last 5 panels for tail. But again, there's no this rule's not set on stone, right? You can modify it accordingly, but I think no matter how complex your wing is, you still can model it within the 5 panels, right? So again, first 5 panels for the wing, it's got a good rule of thumb, and then the last 5 panels for the tail. Okay, so now let's look at the first subsection in here. It's where you include a panel name. The first panel, as I said, it's what basically embedded in the fuselage. The reason is because the panel starts at the fuselage center line, right? And if you have like a flap section in here, you cannot deflect it, right? Obviously there's a fuselage. That's the reason why the first section or the first panel of the wing should have the span as the fuselage radius. Okay. All right. So then you can name the panel accordingly. So maybe like, wing in fuselage or something like that, right? And again, you can specify the aero center of the wing, the aero center X, Y, and Z, right? And the span of the panel, not the entire wing, the span of the panel. This is where you basically enter like half the radius. Well, I guess half the diameter, the radius of the fuselage, right? And then the root chord and the tip chord of that panel and not of the wing, okay? This is just the first panel, right? So all of this specifies to just the first panel alone, all right? So on the number of subpanels, so the way the simulator does some calculations using panel methods. So those of you who took aerodynamics with me know what a panel method is, right? So basically the wings get divided, this panel gets divided into a number of subpanels, and it's a better way to estimate the aerodynamic forces. Okay, so you can set it anywhere from 5 to 10, 5 minimum, 10 max, uh, you can choose that. All right, so now let's look into these parameters here. Okay, again, we are modeling the first panel right now, correct? There's no control surface, nothing, so it's just the whatever the section embedded in the fuselage. All right, so but if when you move to second, third panel, the options are pretty much the same. Okay, you get the same options on all of these panels, right? So let's go over like what are these different parameters mean. So the mount rigging incidence is basically the incidence angle of the wing itself. Okay, so it's like, when you attach the wing to the fuselage, what angle are you attaching at? Is it 0 degrees, 2 degrees, 5 degrees, right? That's basically what you have to put in here. Okay, and remember that you'll be using these panels for modeling the tail as well, right? I mean, you may wonder, well, how you can model the tail with the same panels? Well, it's a horizontal panel. Well, if you change the aero center, to to here, then it basically models the horizontal tail, right? I mean, you still can model the tail in the front, you have a canard, but it's basically the location which which basically says, what it is that you're modeling. You're modeling the wing or the tail, all right? Everything else is the same. Okay, so again, for the tail, it's a tail rigging, like how you're mounting the tail to the fuselage, right? But for the wing, it's how you're mounting the wing to the fuselage, right? So linear twist is basically, what type of twist you have going from the root to tip of that panel right there, right? So that's basically, it's like a geometric twist, all right, going from the root to the tip of the panel, all right? It's really okay. It's a positive linear twist from root to tip, right? Well, I'm sure all of you know what a dihedral is by now, right? The thing is, again, this is a dihedral for this particular panel, and if you have like multiple panels, you can create a wing that looks like that, and it's just like really, really crazy, right? So you got multiple dihedral angles for different panels and so on and so forth, right? If you want anhedral, then you just have to put a negative dihedral, which is basically anhedral, okay? Um, then you have the wing mount effective dihedral angle. So depending on how you mount your wing, in the top wing, in a mid wing, and then the low wing, or high wing and low wing, and the mid wing. So it kind of um, you know it models when you put the wing in these different position, it brings about similar effect as having a dihedral. Okay. For example, if you put a wing on top, like a high wing, then it feels like you have a dihedral of two, and which is why it's a stable configuration. Actually, high wing's a stable configuration. Mid wing is it's neutral, and you have a low wing, which is it's like a negative two, which is like having an anhedral. Okay, so this is like a good approximation. High wing, we can put 2 degrees, right? This is an effective dihedral. And then if you have a mid wing, you can put 0 degrees. If you have a low wing, you can put like negative 2 degrees. Again, this is just an approximation, okay? And that's what the wing mount effective dihedral is. And the effective aspect ratio, now this I should mention, this effective aspect ratio is for the entire wing and not just for the panel, okay? So make a note of that. This effective aspect ratio is for the entire wing and not the panel alone, okay? It's for the entire wing. Okay, so hopefully all of this is clear. Again, you should be finding all of these parameters for that particular panel that you're interested in, and say the only thing is the effective aspect ratio should be for the entire wing. Okay, so in other words, for all of the panels, the effective aspect ratio should be the same, right, for the wing. But for the tail, well, whatever that aspect ratio is, you can put that in there. Okay, so now say you're modeling the second panel. Well, everything, you put all the information necessary for the second panel, the same as we defined here, but you have a trailing edge device, which is essentially a flap, right? Well, if you have a flap, then the way you basically set that is, you see the stage column right here. So you start at like 0, which is basically 0 flap, right? And then you do 1, 2, 3, 4. So this is basically different stages of the flap settings, okay? So then you have the deflection angle corresponding to those stage setting. Well, at 0 stage, the deflection is 0, right? At stage 1, you're deflecting 10 degrees, stage 2, deflecting 20 degrees, stage 3, you're deflecting 30 degrees, right? But, in airplane Cessna, 30 degrees is like the max, all right? So, but you have like 1, 2, 3, 4, 5 rows in here, right? So do not leave this blank. You can just, copy and paste whatever the values you have for like 3, and, you can put that in the 4, okay? That's if you don't have 40-degree flap angle, or, if you don't have like the fourth stage, okay? Just don't leave it blank. All right. So, and then, here you have the CL increment, CD increment, CM increment. Right. So when we say increment, what we are referring to is that, you all know how CL changes as a function of angle of attack, right? So here you can see CL is for a basic section. So once you deploy a flap, it doesn't, well, there's only, depending on what type of flap you have, you can get like different increments, right? But the, you know, it's in XFLR5, you basically get this from XFLR5. In XFLR5, you can only do like this this plain flap. In my experience, I'm not sure if you can do others, but you can do only this plain flap. All right. So what we're trying to do is that, we're trying to get what is that increment in CL as you deflect the angle, deflect the flap at 10, 20, 30 degrees. All right. So this is 0 degree, and then say you deflect it to about, say the plane flap, you deflect to about 10 degrees. You will get a CL increment of, I don't know, like, go from 0.2 to like 0.8. So that's basically the 0.8 that you got to enter, right? So it's the absolute CL. Okay, it's not the it should not be like the difference. You're not adding the difference, but you're saying that's the absolute like CL increment. Okay. Um, right. So this kind of shows this plot shows for different flaps, but what we need is that, when you deflect at flap at 10 degrees, your CL curve shifts up, and then you deflect 20 degrees shifts up, 30 degrees shifts up, right? And you're looking at the CL increment at 0 degree effective angle of attack. Okay, 0 degree angle of attack. What is that increment in CL you're getting? That's what you're inputting in here. Again, I'll create another video on how you can do that from XFLR5, how you can get this information from XFLR5. It's pretty simple, really. If you know XFLR5, doing a quick Google search will actually get you that. So you get CL, CD, and then the CM as well, right? You get that information in, and then you can plug it in here. Okay, that's for flaps. And the same is said for the ailerons. Again, you do the same thing in panel 3. You put all of this the same, but instead of flap, you actually have ailerons, in the outboard section panel 3, right? So when you're defining ailerons or any other control surface like rudder or elevator, then, don't do 0, 1, 2, 3, 4. Do like this, like, 1, 0.5, 0, minus 0.5, and 1. Okay, those are the different stage. And here is the corresponding angle of corresponding deflection angle attributed to that stage, right? So 0 degree, there's no deflection, right? 0. 0.5, it's about 10 degrees, 120 degrees, and negative 0.5, negative 10, minus 1, like negative 20, right? This is just an example. So you have to estimate like what is the max deflection of your control surface. Okay. So again, same as before for flaps. We need that CL, CD, and CM increment from XFLR5. Okay. So, if you notice way back in here, there is this alpha control. Okay. So we talked about this geometry. We talked about trailing edge devices. Let's look at the alpha control now. So the alpha control basically says, you got the alpha control. There are two options here: pitch trim range and then alpha control range, right? So for any control surface, for example, like Cessna, there is a trim tab in the elevator. And you can see the trim tab right here, right? And you operate the trim tab by having this, trim nose wheel. So this wheel, this trim wheel. So you basically like, you trim, you rotate this elevator, this trim tab will basically deflect. Okay, and if your control surface has a trim tab, you can just put that trim range in here. Well, if you notice it as a trim tab, plus or minus 10 degrees is like a good approximation. Okay, then so you have this alpha control range, which is that you're essentially saying the entire tail moves at a given angle of attack at this angle of attack range, right? So that is like a stabilator. If you look at fighter aircraft, so like an F-22, the entire tail moves, right? Um, Again, that's why you got to be careful. If you don't have a stabilator, if you don't have the entire tail moving, just set them equal to 0, right? You don't need it. So, but if you have a trim tab, then you have to put the like range of the trims. Okay, so um, so the last one, if you see here in this section, right, we talked about geometry, trailing edge device, we talked about alpha control. The sweep control, well, again, you don't really need it. You don't have a variable sweep, so you don't really need it. If you have an upper surface device like I don't know, like active blowing or spoilers, you can put that in here. If you have a leading edge slat, leading edge slot or slat, you can put that in here, the alpha increment. But I suspect any of the aircraft that you're going to model have all this. So, but if it has, just you can definitely include them, right? Then the only thing left is the Mach scheduling right here. This is where you put in the airfoil, performance characteristics into the software. Okay, so moving, right here. So you got the Mach number. What I would do is, think of it as a Reynolds number / Mach number dependence. So in XFLR5, if you run the analysis at different Reynolds numbers, well, you get different curves right here, right? So that one of those Reynolds numbers could be for takeoff, one of the Reynolds numbers could be for climb, one of the Reynolds numbers could be for cruise, right? So at different Reynolds numbers or Mach numbers, you get different performance. You basically take that performance and you upload it in a certain format, in these different sections. I'll talk about what type of format you need, to upload these performance parameters into the software, right? So here, the root airfoil and the tip airfoil. So for now, don't assume any aerodynamic twist. So it is possible for you to put, to have a twist in the aerodynamic twist in the panel, each panel. So, but for now, just keep it as constant. Right? And then you get the sweep as well. The sweep is defined as, as you know, this is basically the sweep. If your wing is sweep, and then you basically put what that sweep is for each panel, right? So this is all for like this one panel right here. And as we move to like different panels, you can put either same or different airfoil characteristics. Okay. So that's pretty much it for H panels. Uh, Again, the V panels is exactly the same as you saw in H panels, with actually a little bit less options, which is great, right? So you don't worry about this trailing edge authority or beta authority. We'll talk about that later. But again, everything else is exactly the same. Here you have the rudder, right? The different stages of rudder deflections and the different angles associated with it. And then, the tail airfoils, okay, the vertical tail airfoil. All right. So those are the H panels and the V panels. The only thing left is the control mapping, and then we'll look at some diagnostics. So control mapping is where you specify what control surface lies in what panel. Okay. For example, say here stick X roll, right? So roll, you need aileron to do that, correct? Well, your aileron is in the panel 3, right? So you can see the panel 3 has the value 1 in it, right? So that's how you specify in the software that well, your panel 3 has an aileron. So when you do the stick, you roll, basically deflect that control surface. Okay. For pitch, pitch is in the tail, right? Which is the elevator, and the elevator is in the tail. So again, in this case, the elevator is in like the panel 5, so it has 1. And obviously, the rudder, like the pedals, is not on either of the stick right? So the rudder is in like the vertical panel one, but it has a negative sign because, if you want to turn the aircraft, say, yeah, say, like in one direction, you have to deflect the rudder in the opposite direction to achieve that, right? So that's why you have the -1, in here, right, for the rudder, right? So and then obviously you got the flap. Your flap is in panel two, so you have a put one in here, right? So you don't have to worry about anything else. The trailing edge device kind of takes care of everything. Unless you have a leading edge device, you can turn it on in here as well, right? By just replacing zeros with one. Okay. Um, you don't have to worry about secondary discrete or the rotors or anything, but in the miscellaneous section, it's where you have to specify, like, the pedals. Obviously, the NWS is I guess the nose wheel, or the rudder. So, and then, just keep this red things, whatever it's already in the example file, just keep it the same. Um, right. So, but one thing you have to specify is the left throttle lever and right throttle lever. If you have two engines, you have to make sure the left throttle lever controls the engine one, the right throttle lever controls engine two, and so on. Um, right. So this is where you specify, what, how you control the engines, the throttle. Okay. And the spoiler switch brake, to just leave it as it is. All right. So that's pretty much everything that you need to put, all everything, all the information you need to put the model in the sim. Once you put everything in, there's a quick diagnostic that you can perform. Just do a calculate and basically calculate all these values. Just take a look at this and make sure it's not too off. It's reasonable, and then we should be good to go. Now we'll do some tuning. We'll look at some of the systems, we'll do some tuning, and then we'll get to fly the aircraft. All right, so that's pretty much it. And then in the next video, I'll just talk about how you can use XFLR5 to obtain, the CL increment, CD increment, CM increment for, like, for wings with controlled surface deflections. All right. So, all right, I'll see you in the next video.